the next example. Find the radius and height of right circular cylinder of largest volume that can be inscribed in a right circular cone with radius 6 inches and height 10 inches. Now, this is the scenario then that there is a cone and a right circular cylinder is inscribed in a cone, and the cone has a specific height and specific radius, and we have to um, find out the radius and height of right circular cylinder that can be inscribed in it with the largest volume. So this is the detailed picture. Here R denotes the radius of the cylinder, H is the height of cylinder, and V is the volume. The volume of the inscribed cylinder is V is equals to 4 pi R, V is equals to pi R square H. So this is equation 1. The volume V is a function of two variables R and H. So to eliminate one of the variables in one, we need a relationship between the radius and the height. So using the concept of similar triangles, which we studied in exercise 3.10 in the example when we were doing the problems on related rates. So this is the figure we obtain. These are the two triangles with different heights and different radius. So the height of the cone is 10 inches. The radius is 6 inches, while the radius of the cylinder is R and radius of the cylinder is H. If this is H, then this will be obviously 10 minus H. Now the height by radius of the smaller triangle is obviously equals to the height by radius of the bigger triangle, that is 10 by 6. So writing H in terms of R, substituting the value of H in equation 1, we get V is equals to pi R square 10 minus pi by 3 R. Here V is a function of one variable R. So now let's find the value of R. As R represents the radius and radius cannot be negative, and because the radius of the inscribed cylinder cannot exceed the radius of the cone, so the radius of the cone is 6, so the variable must satisfy this constraint 0 to 6. Thus we have reduced the problem to that of finding the value of the radius in the closed interval 0 to 6, for which the volume is maximum. Since V is a continuous function of radius on the closed interval 0 to 6, the previous method can be applied. So taking the derivative of equation 3, substituting it equals to 0, we are getting two values of radius, 0 and 4. Both of these values are the part of this closed interval, so the maximum must occur at one of these values. Substituting the values of R in the volume expression, we are getting these values. So the maximum volume V is approximately 168 cubic inches, which occurs when the inscribed cylinder has radius 4 inches. And substituting the value of radius in equation 2, we get H equals to 10 by 3 inches. Moving towards the next category, in which there are problems involving intervals that are not both finite and closed. The first example is a closed cylindrical can is to hold 1 liter of liquid. How should we choose the height and radius to minimize the amount of material needed to manufacture the can? So let H be the height of the can, R be the radius, and S be the surface area. Assuming that there is no waste or overlap, the amount of material needed for manufacture will be the same as the surface area of the can. Since the can consists of two circular discs of radius r and a rectangular sheet with dimensions of h by 2 pi r, the surface area will be 2 pi r square plus 2 pi r h. As in can, there are two circular discs whose area is 2 pi r square, and the dimension of the rectangular sheet is 2 pi RH. So since S depends on the two variables R and H, we have to look for some condition in this problem that will allow to express one of these variables in terms of others. Observe that the volume of a can is 1 liter, so it's 1000 cubic centimeters. So it follows from the formula that V is equals to pi r square H is 1000 equals to pi r square H. So we can write H in terms of R. Substituting the value of H in equation 1, we get S is equal to 2 pi R square plus 2000 by R. This is our equation 3. So we have reduced the problem to finding a value of the radius in the interval 0 to infinity, for which S is minimum. Since R is the radius, it cannot be negative, and so can it be 0? Yes, it can be 0, but we won't include 0, because if we'll take the value of R as 0, this term will become infinite. Up till which point we can go? Yes, we can go up till infinity. Since S is a continuous function of radius on the interval 0 to pi, so substituting, finding the limits, we get these values. S does not have a minimum on the interval 0 to pi. Since the minimum must occur at the critical point. Taking the derivative, substituting it equals to 0, I get the value of R, that is 5.4. Since this is the only critical point in the interval 0 to infinity, so substituting the value of R in S, we can get the minimum value of S. So what will be the value of H corresponding to R? Substitute the value of R in the expression H, we get 2R. So this means that minimum occurs when height of the can is equals to the diameter of its base. So how can I say that the value which I got is a minimum? So what I'll do is I can find out this by using the second derivative test. I'll take the second derivative of the function and substitute the value of R in this expression. If I get a positive number, this means that the particular value of R is a relative minimum. So here I'm getting positive value, so this means that the minimum occurs at the critical point, which is this. Now here is another example. Find a point on the curve y is equals to x squared that is closest to the point 18, 0. This is a parabola. We have to find a point on the curve that is closest to this point, which is 18, 0, which is on the axis. So let the distance L between 18, 0 and an arbitrary point x, y on the curve y is equals to x square is given by L is equals to under the radical x minus 18 square plus y minus 0 square. Since this point lies on the curve and xy satisfies this, so substituting the value of y, which is x square, I get this expression. This expression is in terms of x. It is in terms of one variable, as there are no restrictions on x. So the problem reduces to finding the value of x in the interval minus infinity to plus infinity, for which the equation 1 is minimum. The distance L and the square of distance L square are minimum at the value. Thus, the minimum value of L in 1 is this. It occurs at some value. Taking the derivative, finding the critical point, substituting it equals to 0, I get this equation. X equals to 2 is the root, while others are not the roots. So x equals to 2 is the only critical point of the expression. So to determine the nature of this critical point, we'll use the second derivative test. Taking the second derivative, substituting it equals to 0. Taking the second derivative, substituting the value of 2 in the second derivative, I'm getting a positive value which is greater than 0. This means that a relative minimum occurs at point x equals to 2. So substitute this value in the equation y is equals to x square, I get 4. So 2 and 4 are the this ordered pair. This is the point which is closest to 18, 0. Moving towards the application to economics, the three functions of importance to an economist or a manufacturer are the CX, that is the total cost of producing X units of product during some time period. R of X is the revenue from selling X units of products during some time period. And P of X is the total profit obtained by X units of products during some time interval. These are called the cost function, revenue function, and the profit function. If all units produced are sold, then these are related by P of X is equal to R of X minus C of X. That means profit is equal to revenue minus cost. The total cost of producing X units can be expressed as a second degree polynomial. If a manufacturing firm can sell all the products it produces for P dollars a piece, then its total revenue R of X will be R of X is equals to P into X, and its total profit will be P of X is equals to Px minus the second degree polynomial, and during a fixed time period the variable x in equation 4 will satisfy this expression. Now here is an application to an economics problem. A liquid form of antibiotic manufactured by a pharmaceutical firm is sold in bulk at a price of $200 per unit if total production cost for X units is given by this equation. This is the cost function. And if the production capacity of the firm is at most 30,000 units in a specified time, that means value of L will lie between 0 to 30,000. You cannot go beyond this. And how many units of antibiotic must be manufactured and sold in that time to maximize the profit? Now what you have to do is you have to maximize the profit, and the constraint is also given that the value of X can go beyond between 0 to 30,000. You cannot go beyond this value. So since the total revenue for selling X products is 200 into X, 200 per unit, that means 200 into X, the profit P of X on X units will be P of X is equal to R of X minus C of X. R of X is 200x, C of X is given in the expression, it's given in the question. Since the production capacity is at most 30,000, so X must lie in the interval 0 to 30,000. Taking the derivative of the first equation, we get this. Substituting it equals to 0, we get the critical point, and our critical point is 20,000. 20,000 lies in this interval. That means the maximum profit must occur at one of these values. Substituting the values of X in the profit function P of X, we get these values. So the maximum profit is 700,000, which occurs when X is 20,000 units. When X equals to 20,000 units are manufactured and sold in the specified time. Now comes the questions of exercise 4.6, and these are the questions which I have solved for you guys, and you can try to solve them by yourself, and after solving them you can check your concepts by solving the worksheet question.